the issue of the mathematical and numerical models for predicting the ground motion induced by large earthquakes, and how 3D physics-based numerical simulation can be used with the ultimate goals to enhance seismic risk protection strategies. So first of all, let me acknowledge the people that are part of this research. We call us the SPEED group because the code we have developed in the last 8 years is called the SPEED. It's an open source code that is can be downloaded from our website, and is a truly multidisciplinary group. So there are mathematicians, Alfio Quarteroni and Ilario Mazzieri, and our PhD and postdoctoral students. Then there is the engineer counterpart, in particular the group of seismic engineers led by Professor Paolucci. And then there is the industrial counterpart. We have a long-lasting collaboration with Munich Re. Munich Re is the largest reinsurance companies, and it gave us during the last 10 years a lot of requirements and questions and topics on which that we started to study, to carry out this research. So before entering into the general problem and the mathematical details, let me point out the starting points. So this is a table that provided us Munich Re. It's a list of the deadliest events in the last 35 years, both in terms of fatalities and in terms of the overall losses in terms of millions of US dollars. And as you can see, I'm not sure whether you can see it, but there are over 10 major natural events. 6 of them are caused by earthquakes, and in particular the first 2 that caused a lot of fatalities are due to earthquakes and possible consequences of tsunami. And the idea is that, of course, all of you knows that earthquakes cannot predict it, but maybe we can use mathematics to try to study and try to predict the effects of possible earthquakes. So roughly speaking, what is an earthquake? So there is, it's the ground motion induced by the passage of seismic waves. And seismic waves are generated in a point near the Earth's surface that is called hypocenter. And they are generated by a sudden release of energy that has been accumulating through thousands of years. And when seismic waves are generated, they radiate in all directions through the Earth's surface, then through the Earth layers, then they reach the Earth's surface and they become surface waves. The projection of these points onto the Earth's surface is called epicenter. And it's the usual point where earthquakes that took place are visualized over the maps. And in general, the seismicity of an area is expressed by the frequency, type, and size of earthquakes experienced in the past. But what about seismic waves more specifically? So the waves that generates at the hypocenters and radiates through all Earth layers are called body waves. They can be composed, I'll be more precise later on, into primary wave or compressional waves and shear waves or transverse waves. They travel at different velocities. In particular, compressional waves induce a ground motion which is in the direction of the wave is propagating, whereas shear waves induce a ground motion in the plane that is perpendicular to the direction of wave propagations. Body waves, so compressional waves are faster. I'll comment on this in a second, and they travel through all types of materials, including fluids, whereas shear waves travels only through solid media. Once body waves reach the Earth's surface, they become surface waves, and they can roughly be classified into Love's waves and Rayleigh waves. In particular, the most of the damages due to an earthquake are caused by shear waves and surface waves. These are the typical velocity of propagation of shear and compressional waves. As I said, P waves are faster, whereas shear waves are slower, and their difference in their characteristic velocities are usually employed by seismologists to locate the origin of an earthquake. Here it is the main idea I want to describe during my talk, and in general gives also the general flow chart that we follow in our research. So the ultimate goal is to develop and to analyze and to provide suitable models for the enhancement of seismic protection strategies. And the idea is that this can be reached by combining two different ingredients. The first one is we have to be able to predict the ground motion induced by hypothetical earthquakes. Then these 3D-based synthetic scenarios has to be coupled with suitable mathematical models that are able to assess vulnerability of structures, of man-made infrastructures, that means built cultural heritage or even regions of man-made infrastructure like densely populated areas. And if we are able to set up a mathematical model that is able to predict ground motion and then use this data as an input for suitable mathematical models for vulnerability, we can glue these informations and perform a seismic risk analysis. And throughout the talk I will go through the details of first ground motion predictions, and then I'll show you how these results can be used as input for vulnerability models, and then I'll show an example, a full example of how to perform seismic risk analysis. So concerning the prediction of ground motion induced by earthquakes, there are basically two opposite waves that are used within the engineering community, the earthquake engineering community. The first one are based on empirical laws that are called ground motion prediction equations. These are empirical laws that gives the so-called ground motion parameters that are, for example, the peak ground displacement, the peak ground velocity, or the spectral displacement given a kind of soil, a level of energy released, and they have to be calibrated. Then there is the opposite side of the moon. So try to approximate the full ground motion time histories by solving partial differential equations. And as you can imagine, these are very fast, but they have to be calibrated. They are basically 1D ordinary differential equations that are calibrated based on employing registered data. Here you have to solve three-dimensional partial differential equations. And the level, the detail of information required to set up these two different approach, as you can imagine, gets from very simple data that can be acquired from, that are known from seismologists, up to very complicated informations, but these are available these are available from earthquake engineers. What are the main limitations behind empirical models? So this is an example to convince you that somehow mathematics can and partial differential equations can help in the development of suitable mathematical and numerical models to predict ground motion induced by large earthquakes. This plot is a set of data of recorded near fault ground motions that are used to calibrate empirical models. So on the x-axis you see the distance of each dot is an earthquake or a seismic event. So on the x-axis you see the distance from the epicenter. On the y axis you see the magnitude of the event, and any color denotes a different country in Europe, and any dot is a recorded signal. So fortunately, there are a lot of registrations where the epicenter is very far from the place where the signal has been recorded, and of very low magnitude. So this is good news. On the other hand, the shadow region is the range of earthquake that can have a potential damage to structures and to human beings. And you can imagine that if you use this data, and this is actually what is done, to calibrate your empirical models, you might miss some information if you don't have. So the empirical models can be poorly calibrated exactly in the region where you are interested. So the idea is to try to use partial differential equations and discretize them in order to acquire enough information in the range we are interested in. That means large earthquakes that took place very close to the Earth's surface. From the mathematical viewpoint, such a problem can be modeled based on employing the elastodynamic equation. So here U is my displacement, it is a function of the space and the time, and here rho is the medium density that can be supposed to be piecewise constant over my computational domain. This is a datum, geologists can provide us with this data. Sigma is the stress tensor, and I'll describe in a second the constitutive laws we are going to employ to model this term. And then if you don't have this G, you are in the fully elastic case, which is not very realistic for this kind of applications. So the most simplest model you can cook up is to model some sort of viscoelastic behavior by adding a term that is proportional to the displacement itself and to the velocity through a constant C, a piecewise constant C that is a damping factor. And in practical application, this is of order 10 to the power minus 2. And then you have a source term. From the point of view of the model, so for the analysis I will mainly stick on a linear constitutive model. So the stress tensor is related to the strain one through the fourth order Hooke tensor, where as usual lambda and mu are the elastic coefficients, or in certain mainly our Earth is elastic, so this model fits in most of the cases. In certain regions you have to restore to nonlinear elastic models where mu depends on the symmetric gradient, or if you want really to be very sophisticated, you can use a fully viscoelastic model, but then the computational burden becomes really important. Another key point, so this is a wave propagation problem, so you have to pay particular attention to the boundary conditions. So you can impose, so it's very natural to impose a free surface condition on Earth surface, and then from the point of view of the computational model you have to chop your region of interest and add the so-called artificial boundaries. So these of course are there only for the purposes of simulations, and on top of these boundaries we impose a suitable non-reflecting boundary condition in order to make sure that we don't get spurious reflections and refractions. And there are two characteristic velocities that we will see throughout the presentation. This is the characteristic velocity of primary or compressional waves. It can be expressed through the Lamé coefficients and the density, and this is the characteristic velocity of shear waves. Now we can switch from the strong form of our problem, so I'm interested in discretizing my equation based on employing finite element methods. So I go from the strong form to the weak form. This is very classical, and on top of that I want to cook up a numerical model that is able to approximate in space and time my continuous solution. And these are the requirements. So first of all, for such kind of problems, waves are typically propagated over many periods of time. That means that my numerical scheme has to be able to keep under control numerical dissipation and dispersion errors. This is a key point, otherwise I miss all the important information. On the other hand, again, I have a wave problem, so I need high order accuracy also to provide an accurate description of the behavior of my seismic waves at the interfaces. To give you an idea, the typical size of the numerical simulation, so if you want to carry out a real 3D earthquake scenarios, the typical size of the problem, so the number of degrees of freedom can range very easily from hundreds of millions to billions of unknowns. That means that if you want to get results in a reasonable amount of time, you have to make sure that your scheme is highly parallelizable and you have to use high performance computers. And finally, I will comment more on this later on. The geometry involved in such kind of problems is very complicated, and one of the major points is mesh generation. And on one hand, you want to make the process of mesh generation as simple and as fast as possible. On the other hand, you want to be enough flexible in order to generate grids independently for each part of your domain. That means that you want a scheme that can accommodate non-conforming grids and variable approximation order in order to be accurate only in the region where you are enough accurate only in the regions where you are interested. For this reason, we have decided to go for discontinuous Galerkin methods in either their high order fashion or their spectral element fashion. And here is the idea. So I have my computational domain. This is an example of the Grenoble Valley in France. This is a section of the grid of the Po plane. I will show this numerical simulation later on. So the idea is that the geologists provide us and the seismic engineers provide us with the material properties. This is an information that we can access. So I chop my domain into many pieces according to the characteristic velocities of my shear and compressional waves. That means the material properties of the layer of the earth, and I want to create a grid independently for any of my pieces like in a domain decomposition fashion. So I create these grids independently. In any of the subdomains I can go for conforming method if I want. And then at the interface I apply my DG, discontinuous Galerkin paradigm. So I'm going to look for a discrete field that is piecewise continuous polynomial of a given degree within each of the blocks, can be discontinuous at the interfaces, and this has to be I want to look for such a solution for any time t. And if I want to get this goal, I can go for a discontinuous Galerkin method, and this is the semi-discrete formulation. This is quite classical. This is the terms that come either from the damping or it's zero if you are in the fully elastic case. This is the discrete counterpart of my volume term, and in order to make sure that I'm able to control the jump of my discrete displacement, which I recall you can be discontinuous from one interface to the other, I have to suitable penalizing the jump of the semi-discrete displacement and the semi-discrete test function through the faces. This is the so-called symmetric interior penalty that has been proposed by Wheeler and Doug Arnold. And of course you can go, even this is a symmetric formulation, you can decide to go for non-symmetric formulation, just putting a plus here, or even get rid of this term. But our experience with such kind of problems is that symmetric formulations provide better controls in terms of numerical dissipation and dispersion than non-symmetric ones. So here, this is the jump, this is the average. They can be defined morally, rigorously, but roughly speaking, they take into account the jump of your semi-discrete field from one mesh, from one interface to the other, and the average you can take, for example, 1/2 the trace on the left plus 1/2 the trace on the right. And this scheme works provided that you make an appropriate choice of this function that is called a stabilization function. And you can prove that for any time t, your semi-discrete formulation depends continuously on the data in a suitable energy norm that mimics the continuous energy norm, plus you have to add some terms that control the jump of your semi-discrete solution. And you can also prove that you get approximation bounds for your semi-discrete solution. That means that your continuous displacement converges to the semi-discrete one if the solution is sufficiently regular with algebraic rate with respect to the mesh size, so the granularity of the underlying grid, and with also with the expected rate if you increase the polynomial approximation degree. So these bounds are optimal with respect to the mesh size. That means you cannot do better. They are slightly suboptimal with respect to the polynomial approximation degree, but this is known in the DG setting. And everything holds, provided that this magic constant that is put here is chosen sufficiently large. So from the point of view of the semi-discrete approximation, you get stability of your solution and error bounds. And then you can move further, so let's go for the fully discrete scheme. Here you have many choices. The most popular one in the context of earthquake simulation is to go for the leapfrog scheme. This is a second-order explicit conditionally stable method. The reason behind this choice compared to implicit method is that so if you go for discontinuous Galerkin methods, either in their high-order version or in the spectral element fashion, the mass matrix is diagonal. So any step of the leapfrog scheme is very cheap. Basically, it can be carried out fully in parallel. This is the justification from the mathematical and the numerical point of view, but there is also a physical consideration. That is that the phenomenon is very fast. So in any case, if you really want to capture the physics of the problem, you are forced to choose a time step that is very small. So verification. So let's first start with a problem where we know the analytic solution. This is a benchmark in a seismic engineer, is very famous. So the idea is this is called layer over half space. This is a quarter of our domain. It consists of a very tall layer in the bottom and then a thin layer on the top. This is 1/4. You have a seismic source here, and you want to measure the recorded signal here. And you give an excitation in forms of a Richter wave here. And these are the material properties, so the compressional velocity, the shear wave's velocity, and the density. This is our realistic values. And here you measure, so we have run 3 different tests. So on the one hand, we want to compare our discontinuous Galerkin approach with the state of the art for such kind of problems that are fully conforming spectral element methods. And for each, so we constructed 3 different kinds of grid. in the fully conforming spectral element method, you have to construct a regular decomposition into hexahedral elements that is fully conforming. And in order to get a grid of reasonable high quality, you need roughly 150 million degrees of freedom. On the other hand, with the DG approach, given that I can mesh each of my pieces independently, I can play a little bit with the polynomial approximation degree and with the mesh size and go for non-conforming grids. So in the first case, I have hexahedral grids both for the layer on bottom and for the layer on top, whereas in the second test I have X here and tetrahedra here. Here you see the zoom, and they are fully non-conforming. So you can cook up grids that provide reasonable results, saving basically a factor of 5 in the total number of degrees of freedom. And if you measure, roughly speaking, the error, this is formally called relative seismogram misfit, you get reasonable results, but more than this. So I'm not sure whether you can see, but behind the color line there is a black line that is the semi-analytic solution. So you get exactly what you would expect employing only 30 million of degrees of freedom. And this is due to the fact that you can play with the mesh size and the polynomial approximation degree in order to make sure that you have enough points per wavelength given the material properties of your piece of domain. But even if I have such kind of flexibility, for real configurations this might not be enough. To give you an idea, so this is a preview of the simulation I'm going to show you in a second. So we have tried to simulate the earthquake of '99 in Athens. So it's an earthquake that took place in '99 and it was magnitude 6.0. So this is really a multi-scale problem. So I'll show you the details in a second, but to give you an idea, so the simulation, so the grids we had to construct in order to carry out such simulation was roughly 100 millions of degrees of freedom. The whole simulation on the Italian supercomputing center took 4 hours. The process of constructing the grid took 4 months, because the geometry is very complicated and we also want to take into account the seismic response of the Parthenons. So generating the grids is really the bottleneck of the whole simulation. So the idea is then to try to, so it comes from a very simple observation. So DG methods are basically the space where you look for the solution in discontinuous Galerkin methods is the space of piecewise polynomials of a given degree. And you don't have any continuity constraint from one mesh element to the other. So why only considering tetrahedral and hexahedral elements? Can I go for arbitrarily shaped decompositions? So this observation is part of a huge research that is has been carried out starting from 10 years, maybe less, on developing numerical schemes that can support meshes made of arbitrary shaped elements. So discontinuous Galerkin methods is one of the examples, but then there are virtual element methods, mimetic finite differences. So to overcome possible limitations provided by tetrahedral and hexahedral grids. And the idea is that DG method seems to be naturally well suited to support arbitrary shaped elements. They are naturally well suited for high order approximations, and the dimension of the space of your local polynomial space depends only on the desired accuracy. That means the polynomial degree, and not of the shape of the underlying element. And for this reason, this is the main idea we have, we want to follow. So we have our this is a cartoon, but gives the idea. So we have a complicated geometry, and we don't want to spend months in trying to construct a grid made of hexahedral or tetrahedral elements. So and on the other hand, seismic engineers like very much Cartesian meshes because they are very easy to be handled and they provide very useful information. So the idea is that you construct a background grid made of tensor product elements, and then in order your mesh, since you want your mesh to fit the underlying geometry, like the jump in the material properties, you just chop elements. In such a way, near the regions where you have discontinuities of the material properties, you end up with elements that can have any arbitrary shape. And you can imagine that you can really get crazy elements like with the generating faces or even a very large number of faces, but DG method, the theory of DG method can be extended to cover also these cases. And so all the analysis I've shown you before for the elastic wave equation can be extended to arbitrary shape elements. I'll show you some results in a second, but we have also tried to face other kinds of problems, because we have in mind that maybe if you have a moving domains or interfaces that are possibly moving in time, you can really chop elements. Like here, this is the evolution of an ideal blood cell that is undergoing large displacement. So at each time of my simulation, I just chop elements in order to fit the underlying geometry. And you can even handle situation where you model not only the fluid structure interaction problem, but also include suitable models to take into account possible contact between the structures based on a penalty formulation. Or you can go for fluid flow problems in fractured porous media, where here also in these cases the geometrical complexities is most of the time the bottleneck of the old simulations, because in reservoir simulations you might have thousands of possibly intersecting fractures and you have to encode them in your computational geometry. So now, going back to wave propagation problems, so one of the key points is to make sure that your scheme, so we have shown that it is stable, that it provides optimal approximation bounds in H and slightly suboptimal with respect to the polynomial degree. But one of the key points is we have to make sure that numerical dispersion and dissipations are under control. So numerical dissipation is basically the difference in the peak between the true wave and the simulated one. And numerical dispersion is the numerical error induced in the phase. If you miss these informations, you miss all the important information. So numerical dissipation and dispersion must be reasonably low in order to make sure that you are really getting the most important features of your problem. This analysis is quite classical, can be carried out based on employing a plane wave analysis that you let propagate through an infinite unbounded isotropic medium. So we have carried out both in 3D, and we have also tried to investigate how the shape of the elements influence numerical dispersion and dissipations. And it turns out that, so first of all, the first good news is that this is the relative dispersion errors obtained with the spectral element methods, so the state of the art for earthquake simulations based on employing conforming hexahedral and tetrahedral grids. And these are the same kind of results obtained based on employing discontinuous Galerkin methods. And they provide comparable dispersion errors provided you have enough points per wavelength. And this is exactly what you would expect. So if you have enough points per wavelength, you are sure that your dispersion and dissipation errors are below a given tolerance that is usually set at equal to 10 to the power minus 6. So now let's go for validation. So I'm going to present you two examples of real earthquakes and show how we are able, with the proposed approach, to fit the data recorded by the seismogram. The first one is the event that took place in 2012 in Italy, in the Po Plain in the north of Italy. It has been a huge earthquake, and it is estimated the overall losses in terms of economy is around 5 billion. This is the numerical scheme, so it's the region we are simulated is roughly speaking 20 kilometers by 74 by 51. This is Mirandola, that was the town that was more close to the epicenter. This is the picture. So this is the slip distribution. This is the measure provided us by the seismic engineers that tells us how much the fault has moved. And these are the characteristic velocity of the soil behind Mirandola. And as you can see here, there is a sedimentary basin very close to Mirandola. One single simulation took approximately 150 millions of degrees of freedom if you want to go up to 1.5 Hertz. If you want to go to higher frequencies, then the models blows up very quickly. And it took roughly 5 hours on the Italian supercomputing centers. And these are the comparison between the recorded signal and the simulated one. More precisely, the black lines, so for each of the 3 components of the velocity, so up, north, south, and the other one is west, east, and for each of the 7 selected sides, so each sequence of letters and numbers uniquely identifies a place where a seismogram is placed. So for each of the 3 components of the velocities, you can see that there is a good agreement between the recorded signal and the simulated one. So somehow the results we obtain, of course they are not perfect, but this cannot be, I mean the phenomenon is much more complicated, but we are able to capture the main physics of the problem. And this is a video that shows, so this is the region, Mirandola is here, this is the main site. So this is the computational domain, so the artificial blocks, so this is the stratigraphy. These are the characteristic velocity of the soil, and here you can clearly see this is the peak, the magnitude of the velocity. You can clearly see that the body waves reach the surface, and just want to make another comment. They reach the surface. Ça va? Their body waves reach the surface. They get transformed into surface waves, and as I said, there is an alluvial basin very close to Mirandola, and you can clearly see that, as expected, the waves remain entrapped within the soft soil, and this is what caused most of the damages during the event near Mirandola. So here they become surface waves, and then they remain somehow entrapped within the soft soil. The second example is, as I already mentioned, the earthquake, the Athens earthquake of '99. Again, is magnitude 6.0, so pretty huge earthquake. And I decided to present this example because it really gives you an idea of the different scales that are involved. How much time do I have? 20 minutes. Okay, thank you. So this is the computational domain, 30 kilometers times 35 times 39. Each color denotes different soil materials. So these are the characteristic compressional waves velocity, and these are the characteristic shear waves velocity, and these are the different density. And on top of that, there is the Acropolis, and the zoom is here. So the dark green here is the Acropolis, and this is the surrounding region. So here we go from 30 kilometers to the scales of a few meters. And on top of that, you might want to simulate, to take into account also the dynamic response of the Parthenon, so the interaction between the soil and the Parthenon. And if you really want to simulate the seismic response of man-made infrastructure, you have to go up to 5 Hertz. So you have to increase the range of frequencies. And so for the moment, this is the best we can do. But in order to really to be realistic, we should be able to go from 5 up to 15 Hertz in order to really study the full seismic response. And these are the parameters of the mesh. So the characteristic size of the mesh size in meters. So if you have to go from ranging from 5 meters up to 700 meters, so each element has this characteristic size, and you can play also with the polynomial approximation degree in order to make sure that in each of the regions, given the material properties, you have enough points, interpolation points per wavelength of interest. And this is the computational grid of the Parthenon, and here the characteristic size is 0.5 meters. So you really have a huge variation in your discretization parameters. But you can generate the grids independently and then match them irrespectively of how they get in contact from one interface to the other. And these are some snapshots of the velocity magnitude at different time steps. And this is the video that shows the peak ground. So the color is the peak ground velocity. The displacement is the computed displacement. It has been magnified just for the purposes of visualization. And the Acropolis is on top of here. Now, I think I'll switch this part. The only point I want to make is what happens if an earthquake took place near a coast or near a coastal environment. Of course, from the mathematical viewpoint, since we know that only compressional waves propagate through fluids, we cannot no longer use only the elastodynamic equation. So the idea in this case is to use an heterogeneous model where you couple an elastic medium with an acoustic one, and you want to simulate the propagation of waves through coupled elasto and acoustic media. The idea is that you write down your equations. These are exactly the same equations I discussed before, and in the acoustic medium you solve with respect to acoustic potential. That basically means you solve a wave equation. And you have to make sure that you properly prescribe the interface condition in order to make sure that the physical properties are satisfied. But this in the DG framework can be done, and can be done based on exploring the fact that your discrete displacement and your discrete acoustic potential do not have to match continuously because they are allowed to jump at the interface. So you can basically prescribe in a weak sense that the normal component of the velocity field is continuous. And you can write down the model. Basically, the two bilinear forms that end up after discretizations looks very much like those I presented before. And you can extend the theoretical results in the fully coupled problem, and you get exactly what you would expect. So you get a convergence estimate that is as before for the elastic part, and something that looks very similar in the acoustic one. And I'll skip this part. This is the propagation of a wave into an elastic medium with an acoustic inclusion. But the reason why I presented this part is just because I want to show you an example where polytopic grids can really play a major role. So this is an example where you have an elastic material with many acoustic inclusions. And of course, if you want to really resolve all the acoustic inclusions, the characteristic size of your grid has to be comparable to the diameter of these small holes. On the other hand, if you allow for polytopic elements, so arbitrary shape elements, you can decide that this is only one mesh element for the acoustic region. And even if you keep on refining the elastic one, you still keep here one element for the acoustic inclusion with many edges, but this is not a problem. You just increase the polynomial approximation degree here in order to make sure that you approximate your acoustic potential with enough accuracy. And this is one of the examples where polytopic grids can really provide a smart solution for problems that contains many inclusions of characteristic size that is much smaller of the background domain. Now, last 10 minutes on how I can use the 3D ground motion scenarios in order to, in combination with suitable vulnerability models. So the idea is that my 3D simulations can be used as input in suitable vulnerability models. And what we decided to do is to use one of the most used approach for quantifying the vulnerability of structures. And these are called seismic fragility curves. These are curves that, given the spectral displacement, which I'll define precisely in a second, gives you the conditional probability of having a certain level of damages for any kind of man-made infrastructure. So for each kind of buildings, for example, the year where the building has been, when the building has been constructed, the number of story, the material of constructions, these are available from structural engineers, and tells you that, for example, a high tall building like more than 20 floors or more than 100 meters can be subjected to either a complete, extensive, slight or moderate damage if it undergoes to a spectral displacement of a given magnitude. And this can be used to perform vulnerability of structure if we know that for a given earthquake or a given possible earthquake scenario, we would expect a spectral displacement of that size or of that size. And the idea is that spectral displacement can be computed started from 3D numerical simulation. Is one of the quantity that can be computed based on employing post-processing. And the idea is the following. So roughly speaking, the spectral displacement is the maximum relative displacement of a building that is subjected to a given shaking of the ground. It can be computed starting from the time history, simply solving a 1D ordinary differential equations that take as input the ground displacement, solve a very simple 1D model, and gives as output the spectral displacement. And this, of course, can be done for any possible realization of a possible earthquake, and for any kind of man-made infrastructure you can measure, you can compute the conditional probability of having a given state of damage. And in order to demonstrate how to couple the 3D simulations with vulnerability curves, let's go through an example. So this is a test case we carried out in Beijing metropolitan area. So under Beijing there is a very huge fault that is the black line reported here. So we have considered a box in the surrounding that surrounds Beijing. We carry out 30 different scenarios that have been obtained ranging the magnitude, the possible magnitude that is compatible with this kind of fault. These are a range that has been provided to us by earthquake engineering, varying the fault mechanism rupture and varying the hypocenter and the location of the rupture. So 30 possible realization of earthquakes in the metropolitan area of Beijing. Each of the simulations involve roughly 160 million of degrees of freedom and took 12 hours on the Italian supercomputing centers. Then we have, for each of the 30 possible realizations, we computed the spectral displacements in a number of selected points. So Beijing is here. This is the projection of the fault. And we have then collected all the possible spectral displacement in terms as a function of the distance from the rupture point. And based on the computed spectral displacement, we have carried out the seismic risk analysis for tall, high-rise buildings, so over 100 meters high. And these are the conditional probabilities of complete extensive moderate lights and null damages as a function of the distance from the rupture point. And this can be used to assess the overall vulnerability of high-rise building in the metropolitan area of Beijing. So to have an idea of how strength are those kind of buildings, given possible realization of a large-scale earthquake. And now I think I can go to the conclusions. So I show you that there are so at least to me, very interesting challenges behind the problem of trying to simulate 3D physics-based scenarios to be employed as an input for seismic risk analysis. There are still a lot of things that we want to do and we are planning to do. First of all, including also nonlinear acoustic problems, so switch from linear to the fully linear elastoacoustic to non-linear elastoacoustic wave propagation problems. Then there is a major issue that even if our approach seems to be competitive from the point of view of trying to keep the computational cost as low as possible without, of course, deteriorating the accuracy, there is still a limitation on the maximum frequency we can get. Because if we really want to go to high frequencies, the computational border is too high, at least for the machines and the technology we have right now. So the idea is try to make use of artificial neural networks and to somehow get some information for high frequencies without doing the full simulation up to 100 Hertz. And then exploiting further the flexibility of polygonal polyhedral meshes and mount on top of the simulation suitable agglomeration-based procedure in order to make sure that if we need a solver, we can exploit multi-level and multi-grid solution techniques, and then incorporate in our model. So this is very challenging, the dynamic fault rupture. So for the moment, all our simulation so we use as input data the slip distribution. So it's like if the earthquake starts at the time T0 plus epsilon. So the great challenge would be to incorporate in the model also the mechanism of fault rupture, which of course has completely different time scales with respect to the seismic wave propagation problem. And let me acknowledge the fundings that support our research. Thank you for your attention.
Paola, for your interesting results. Are there questions or comments? I have. Oh, sorry. No, go ahead. Go ahead.
I was wondering, have you use structure of the ground from geologists or whatever? And I wondered whether you could use your code to check whether their structures solve the inverse problem. Have you thought about solving the inverse problem?
Thank you for your question. That's absolutely a good point. Yes, it's one of our dreams to go, because of course we trust them for the moment on the quality of their data, but of course they are affected by a lot of uncertainty. So one of the next steps, but this is a long step, is to go for inverse problems to make sure that the data they provide us are correct, not only in the material parameters, but also, for example, in the fault position, because they have a guess where the fault is, and this is of particular importance, for example, also in oil extraction. So solve an inverse problem in order to make sure to locate correctly the present and the position of a fault. This is very challenging because the problem is huge and the inverse problem is even more huge, but it's on our wish list on a long scale.
So you mentioned that the meshing was sort of the bottleneck for all this. So when you say it took 4 months, was that actual 4 months of computing time, or was this
going
out and taking
4 months of one of us that took the data, took the CAD of Parthenon, took the data from the geologist, set up the model, then did the grid, then make sure by propagating, for example, a plane wave, that the grid is sufficiently fine, and then make sure that in the process of gluing all the pieces there are no holes. 4 months of true work. Not 4 months of compute. That would be okay. I mean, you just press a button and it works.
Has there been any thought of using like isogeometric methods to work with the CAD models directly?
Yes, it's a possibility, absolutely. The point is that I mean, you can go for isogeometric to mesh and to work with the single pieces, and then you would need, in any case, to glue everything with either a DG or a mortar or whatever you want. That's a possibility, absolutely.
Other questions? No, I'm just curious how these results are used by engineers.
So there are two answers. So seismic engineers, they use these results to as an ingredient for vulnerability curves that are exactly their job. So for the moment they use vulnerability models, but they feed where it is. They feed this line based on employing, so they realize what kind of spectral displacement you can get based on employing empirical models. So the idea, the end of the game is always to try to understand for a possible realization of earthquake which kind of spectral displacement you would get. So for the moment they use, well, up to some years ago they used to use empirical laws in order to say, okay, if an earthquake takes place in the pop plane, I would get a spectral displacement between 1 and 1/2. The idea is that, and then based on this, they know whether a certain area is at risk or not, because if you have most of the buildings that are at high risk of complete failing, this is a problem, and this can be used, for example, to make sure that you reinforce that buildings.
For new construction.
For new construction, for example. So every construction right now has to be designed in order to for a certain spectral displacement that I would say that is between 1 and 1/2, to undergo to an extensive damage but without a complete fail. So this is the rule any seismic engineer and any structural engineer has to obey in designing new buildings. For the already existing buildings, if you know that there's a region of your city where most of the buildings might fail completely, you might take any action and reinforce the construction. So the idea is to replace, so what we are doing right now is to replace empirical models that are used to locate in which point of the x-axis you might fail with the simulations. Reinsurance companies make a completely different argument, but this is because they draw from, I mean, they have an economic exposure, so they use simulation to increase their database. So they have an hybrid recorded simulated database, and then on top of that they have their magic rules in order to quantify how much they are exposed.
Have you tried this out in Los Angeles?
Sorry?
We tried this out in ground in the around Los Angeles?
Not yet. This is only 1 week, so we need slightly more time. But of course there is a huge research in that area. I mean, the US Geological Service is very active, and they have great research groups that are working on this topic as well.
Can you say something about the real order of the polynomials that you have used in the simulation? And
No, between 3, never lower than 2, except for man-made infrastructure for buildings, not higher than 6. So the polynomial degree we use in practice range from 2 to 6. This because I mean, this comes from a consideration of numerical dissipation and dispersions. So we already know that for the typical frequency we are interested in at least up to 2.5 hertz. If you have at least a polynomial of degree 4 or 5, you are sure, at least in the ideal case, that your dissipation and dispersion error are below 10 to the minus 6. So that's this seems to be a good compromise between accuracy, computational cost, and control of the numerical dispersion and dissipation.
There are no more questions.
Thank you. Thank you.
There is a wine.